Hello, good day, everybody. We are welcome once again to the lecture of Chemistry 235. That is Basic Organic Chemistry. My name is Mubarak Oloduwo Amin, and I've been your tutor since the beginning of this class. Today, we want to discuss the second part of the factors affecting structure and physical properties of organic compounds. Today, we'll be looking at the physical properties and functional groups. At the end of today's lesson, you should be able to explain the physical properties of alkanes, alkylides, ethers, amines, and alcohol. Also, you should be able to explain why the boiling point of primary and secondary amines are higher than those of alkanes or ethers of similar molar mass, but are lower than those of alcohols. Also, you will be able to compare the boiling point of tertiary amines with alcohols, alkenes, and ethers of similar molecular mass. And also, you should be able to compare the solubilities in water of amines with the solubility of comparable alkanes and alcohols in water. So, let's go. Physical properties and functional groups. Compounds that contain very similar atoms can have very different properties depending on how those atoms are arranged. This is especially true when they have different functional groups. I shall start with alkanes. Alkanes, as we all know, they contain only carbon and hydrogen. They are comprised of relatively weak forces holding the molecules together. The molecules of an alkane are held together by induced dipole interactions, which are also known as the van der Waals forces. These interactions are the weakest of all the intermolecular attractions, and in order for alkane to boil, the van der Waals forces must be overcome. The magnitude of the van der Waals forces that hold alkane molecules together depends on the area of contact between the molecules. That is, how the molecules fit together. The greater the area of contact, the stronger are the van der Waals forces, and the greater is the amount of energy needed to overcome those forces. If you look at the homologous series of alkanes, you see that the boiling point of alkanes increase as the size increases. This relationship holds because each additional methylene group increases the area of contact between the molecules. The four smallest alkanes have boiling point below room temperature, so they exist as gases at room temperature. Pentane, with the boiling point of 36.1 degree, is the smallest alkane that is liquid at room temperature. And this table shows the boiling point and melting point of alkanes, the first 13 alkanes. If you look at the boiling point, you notice that it increases from methane down to tridecane. Similarly, the melting point also increases in a similar manner, and also we also have the density here. You notice the trend in the density; it also increases, showing that the melting point, the boiling point increases as the number of chain increases. Melting point is the temperature at which a solid is converted to a liquid. Melting points of alkane increase with a few exceptions in homologous cells as the molecular weight increases. The increase in melting point is less regular than the increase in boiling point because packing influences the melting point of a compound. And what is packing? Packing is a property that determines how well the individual molecules in a solid fit together in a crystal lattice. Let us look at the table again to look at the melting point, okay, to see what we mean. These are odd number alkanes. C3. Okay, they're not just odd number. Yes, C1, C2, C3, C4, C5, C6. Now, if you compare the melting point and boiling point, you notice that the boiling point steadily increases. But in the case of the melting point, the increase is not that pronounced as compared to boiling point. This is due to the fitting of the crystal lattice as explained here because of packing in the crystal lattice of the molecules of alkane. The tighter the fit, the more energy is required to break the lattice and melt the compound. Alkanes with an odd number of carbon atoms pack less tightly because the methyl group at the end of their chains can avoid those of another chain only by increasing the distance between their chains. Consequently, alkane molecules with odd number of carbon atoms have lower intermolecular attraction and correspondingly lower melting points. Density also increases with increasing molecular size, as you can see in the previous table. Similarly, flash point increases with increasing chain length, meaning that the longer the chain, the chain are less flammable. That the longer chains are less flammable. Branching in a compound also lowers its boiling point because it reduces the area of contact. For example, if you look at the example we have here, we have pentane, isopentane, and neopentane. And if you compare their boiling point, you notice that the neopentane, which has maximum branching, has the lowest boiling point. This is how branching uh, affect boiling point of substance, as we have discussed previously. Now, alkyl halides. Alkyl halides are also known as haloalkanes. These are compounds in which one or more hydrogen atoms in alkane have been replaced by halogen atoms, fluorine, chlorine, bromine, or iodine. And the example is given here. This is a situation where one hydrogen has been replaced by chlorine in a methane. And we call this one chloromethane. And this is dichloromethane, trichloromethane, and tetrachloromethane, where all the hydrogen atoms have been replaced by chlorine atom. These are alkyl halides. There is van der Waals dispersion forces in alkyl halides. This attraction gets stronger as the molecules get longer and have more electrons. That means as the chain increases, the van der Waals forces also get stronger. Halogens, fluorine, chlorine, and bromine are more electronegative than carbon. Therefore, the carbon atoms that carry halogen are charged partially positive, while the halogen is charged partially negative. As you can see here, this is halogen, this is carbon, partially positive, partially negative. So there's a dipole attraction operating in alkyl halide in addition to the van der Waals dispersion forces. This means that in addition to the dispersion, there will be dispersion forces. There will be forces due to the attraction between the permanent dipoles. The size of those dipole attractions will decrease as the bond gets less polar, as you go from chlorine to bromine to iodine. The more halogen are substituted, the less volatile the alkanes becomes. That is, if you have more halogen in a molecule, they become less volatile. Volatility, this is the tendency of a molecule at the surface of a compound to enter the gas phase. The more volatile a compound, the more likely this is. For every extra chlorine atom on the original methane molecules, the volatility of the compound decreases. This can also be observed by the increase in both the melting point and boiling point as one goes from chloromethane through to tetrachloromethane. The more halogen atoms in the compound, the stronger the intermolecular forces are, which leads to higher melting point and boiling point. As you can see here, chloromethane has a melting point of minus 97 and a boiling point of minus 24. Dichloromethane has a melting point of minus 96, Okay, it increased. While dichloromethane has a boiling point of 39, you can see from minus 24 to 39. You can see the increase in melting point. Trichloromethane has a melting point of minus 63.5 and a boiling point of 61.2. So generally, as the number of halogen atom increases, the melting point and boiling point also increases. Here also we have the boiling point of different alkyl halides. Here, if methane, that is, if the fourth member of this is methane, it's hydrogen, you have methane. The boiling point is minus 61.1 minus 161.7. While if the hydrogen has been replaced with fluorine, it is minus 78.4. That is an increase. If it's a chlorine, minus 24.2. If it's bromine, 3.6. And iodine, 42.4. This also show that the boiling point increases as you go from fluorine to iodine. Also, when you go down, you notice that as the chain length increases, the boiling point also increases. This is also true for the halogen. As you go down, here you have a one carbon atom. This is two carbon atom. This is three carbon atom, and so on and so forth. So the boiling point increases from fluorine to iodine, and it also increases as the number of chain increases. The boiling point also decreases as the isomer go from a primary to secondary to tertiary halogenoalkane. Okay, we are talking about branching now. Branching. This is a simple result of decrease in the effectiveness of the dispersion forces. Okay, this is a straight chain halogen alkyl halide, bromobutane. This one is 2-bromobutane, and this one is 2-bromo, 2-methyl-penthane. They all have the same molecular mass. But look at their boiling point from 375, 364, 346. You can notice that as the branching increases, the boiling point also decreases. So branching, this is how branching affects the physical property of organic compound. Solubility in water. Alkyls have little or no solubility in water. In other words, they are slightly soluble in water generally. For alkyl halide to dissolve in water, you have to break attraction between the halogenoalkane molecules, okay, and break also the hydrogen bond between water molecule. For this breakage, you need energy. Solubility in organic solvent. Alkyl halides tend to dissolve in organic solvent because the new intermolecular attraction have much the same strength as the one being broken in the separate halogenoalkane. Now, let me go further here. The solubility in water is slightly, uh, they are sparingly soluble in water because, in addition to the van der Waals forces in halogenoalkane, you also need to break the forces in the hydrogen bond in water before the molecules can mix together for them to be for the halogenalkane to be soluble in water. The energy required to break the hydrogen bond is much higher than the energy it will require to mix together. Thus, alkyl halides are sparingly soluble in water. In fact, as the number of carbon chain increases, the solubility rapidly decreases. Also, ethers. We also talk about ethers. Ethers are a class of organic compound that have an oxygen atom attached to two same or different alkyl or aryl groups. We can write the general formula of ethers as this. Okay, alkyl attached to oxygen, or alkyl and aryl attached to oxygen, or aryl attached to oxygen. In ethers, both van der Waals forces and dipole-dipole interaction must be overcome for ether to boil. Thus, ethers generally have higher boiling point than the alkanes of comparable molecular weight. The miscibility of ethers with water resemble those of alcohols. That is, the lower ethers are soluble in water, and as the number of carbon chain increases, the solubility decreases. Amines now. Amines are organic compounds which contain and are often actually based on one or more atoms of nitrogen. In an amine, one or more of the hydrogen atoms from ammonia are replaced by organic substances like alkyl and aryl aromatic. Hydrogen bonding significantly influences the properties of primary and secondary amines, as well as the protonated derivatives of all amines. So in amines, hydrogen bonding operates apart from the van der Waals due to the chain length and also the dipole between nitrogen and carbon. And here you have a typical primary amine in which two hydrogen atoms are attached to the nitrogen. Then you have a secondary amine, one hydrogen atom attached to nitrogen, and in tertiary amine, it has no hydrogen atom. And that is why you don't have hydrogen bond in tertiary amine. But you have hydrogen bond in secondary and hydrogen bond in primary. Nitrogen is not as electronegative as oxygen, which means that the hydrogen bond between amine molecules are weaker, not as strong as the hydrogen bond in alcohol. An amine, therefore, has a lower boiling point than alcohol with a similar molecular weight. Because primary amines have two nitrogen-hydrogen bonds, hydrogen bonding is more significant in primary amines than in secondary amines. Tertiary amine cannot form hydrogen bonds between their own molecules because they do not have a hydrogen attached to the nitrogen. Okay. Consequently, if you compare amines with the same molecular weight and similar structures, you will find that primary amines have higher boiling point than secondary amines, and secondary amines have higher boiling point than tertiary amines, as you can see here. This is an example of a primary amine with boiling point of 97 degrees Celsius. This is an example of a secondary amine with boiling point of 84 and a tertiary amine with boiling point of 65. You can see that the boiling point decreases as you go from primary to secondary and to tertiary. Most aliphatic amines display some solubility in water, reflecting the ability to form hydrogen bonds. Solubility decreases relatively proportionally with the increase in the number of carbon atoms in the molecule, especially when the carbon atom is greater than 6. Aliphatic amines also display significant solubility in organic solvents, especially in polar organic solvents. In other words, amines, the solubility decreases as the number of carbon chain increase. Because of the ability to form hydrogen bond, amine shows solubility in water. And this chart here shows the hydrogen bond formed with water. Okay, this is water, oxygen, hydrogen, forming hydrogen bond with the hydrogen of the nitrogen atom, as you can see here. Also, okay, here is the amine molecule forming hydrogen bond between themselves. This is how they form hydrogen bond. Alcohols now. An alcohol is an organic compound with hydroxyl functional group on aliphatic carbon atom. Because hydroxy is the functional group of all alcohols, we often represent alcohols by the general formula ROH, where R is an alkyl group. Methanol and ethanol are the first two members of the homologous rings of alcohols. An alcohol has both a non-polar alkyl group and a polar hydroxyl group. As the alkyl group increases in size, it becomes a more significant fraction of the alcohol molecule. In alcohol, there are hydrogen bonds as well as van der Waals operating in the molecule. The compound becomes less and less soluble in water as the number of hydrogen atoms, number of carbon atoms increases, number of chain as the chain increases. The hydroxyl group generally makes the alcohol molecule polar and therefore more likely to be soluble in water. However, the carbon chain resists solubility, so there are two opposite trends in the alcohol. Alcohols with shorter carbon chains are usually more soluble in water than those with longer chains. Four carbon tend to be the dividing line at room temperature. Alcohols with fewer than four carbon are soluble in water, but alcohols with more than four carbon are insoluble in water. In other words, an hydroxyl group can drag about three or four carbon into solution in water. However, the solubility of alcohol also depends on the structure of the alkyl group. Alcohols with branch alkyl groups are more soluble in water than alcohol with non-branch alkyl groups with the same number of carbon atoms. Branching minimizes the contact surface of the non-polar portion of the molecule. So tertiary butyl alcohol is more soluble than normal butyl alcohol in water. Also, because of hydroxyl group, all three pentanol molecules have a greater solubility in water than ethane. Ethanol is completely soluble in water in any amount. In all proportions, ethanol is soluble. This is because it contains a hydroxyl group and has much shorter nonpolar chain length than pentanol. Alcohols tend to have higher boiling point than the hydrocarbons because of the strong hydrogen bond between hydrogen atoms of one hydroxyl group and the oxygen atom of another hydroxyl group. In other words, because of hydrogen bond operating in alcohols, they have higher boiling point when you compare them to alkanes and other class of organic compounds such as amines or ethers. This table, this chart here illustrates the hydrogen bond between water and an alcohol, while this table shows the boiling point of few selected alcohols from methanol to dodecanol, an alcohol with 12 carbon atoms. This table here compare the properties of alkanes, ethers, alcohols, and amines. Their properties, especially the boiling point. If you look at the boiling point of propane, for example, is 42.1. Ether, that is dimethyl ether, 23 minus 23.7, it increases. Alcohol, that is methanol, 78, whereas ethyl amine is 16.6. Here, alcohol has the highest uh, boiling point when you compare them with alkane, ethers, and amines. Similarly, if you go down, you notice that the boiling point increases. Okay, if you go down the table, it increases. If you go from left to right, it also, sorry, from left, let me say generally, alcohols have the highest boiling point. They have higher boiling point than the amines. In summary, in this lesson, we have learned that the boiling point of alkanes increases as their sizes increases. The increase in melting point of alkane is less regular than the increase in boiling point because packing influences the melting point of a compound. The density as well as flash point of alkanes also increases with increase in molecular size. Because of the presence of dipole, alkyl halides ethers have comparatively higher melting point and boiling point than the alkanes. Because of the presence of hydrogen bonds, amines and alcohols also have comparatively higher melting and boiling point than alkanes, alkyl halides, and ethers. Solubility of this organic compound also follow the same trend. That is, solubility decreases as the number of carbon chain increases. Okay, because as the number of carbon chain increases, the non-polar characteristics increases. So solubility decreases. However, alcohols are more soluble when you compare with the other organic classes. We also learned that intermolecular forces play important roles in the physical properties of organic compounds. How weak or strong these forces are will dictate the nature as well as how easy a substance will boil, melt, dissolve in water, and so on. I hope you have grabbed one or two things from our lesson today, talking about the physical properties of organic compounds. You can consult this site if you want to learn more or to understand better on the physical properties of organic compounds. Happy see you next class.